Let's take a look at Ceres Rc Circuits, where we're now looking at the resistance, reactance, and the impedance. Again, you can see in every case we're using these vector diagrams that you see across the bottom, and you've already been introduced to the reactance, capacitive reactance relationship 1 over 2 pi fc. So now we're going to put it to use, and again, put it together with the complex numbers, the vectors, phasors, and the relationships as we start plotting their values. So since the VR, drop across the resistor, and the current are in phase for a typical circuit, R is always plotted across the x-axis. X sub c, the reactance for the capacitor, must be plotted along the negative y-axis or the minus j-axis, we use them interchangeably, to show the 90-degree phase difference between capacitive values and resistive values. So what we're going to start seeing here mathematically is as we start putting in values for this simple RC circuit, we're going to see how the vectors change and the resultant values for the impedance Z and the total supplied voltage. So another example, we're going to take a simple RC circuit where we're going to have a 2K ohm resistor and a 20 nanofarad capacitor. Now we start introducing the frequencies in here. So F is equal to 3K hertz, and they want us to find the capacitive reactance, the total impedance, and the angle theta. So we're going to start with that relationship. X sub c is equal to 1 over 2 pi fc. Since we have all of the values given, we can calculate for the capacitive reactance. So 2 pi times 3K hertz times 20 nanofarads. Invert that, you get 2.65 kilo ohms, 2.65 k ohms of resistance associated with the reactance. Okay, this is the imaginary portion here, the reactive component. So again, we pick one of our trigonometric functions that matches the sides of the triangle for which we have values. So tangent theta, the opposite side over the adjacent side. Remember that SOHCAHTOA relationship I gave you? So tangent is equal to opposite over adjacent, or in this case, X sub c over R for our right triangle. So X sub c, we just calculated here, 2.65, and 2K ohms gives us a minus 1.33. Why did we get a negative here? We didn't get a negative up here. Well, because we know it's going to be along that negative j-axis. So sometimes the angle takes care of it. Sometimes you can force it and put the value in here. So we're going to add the negative. So negative 1.33. If we take the inverse tangent of negative 1.33, we get an angle of minus 53 degrees. Again, that counterclockwise angle from the x-axis. We pick another trigonometric function. Cosine theta is equal to the resistance then over the total impedance. Remember, we're dealing with both of these relationships, these vector diagrams. Now we're on this vector diagram over here. So R over Z, we knew the value of R, 2K ohms, and we just are calculating for Z. So we took this relationship, we manipulated it, we're solving for Z. The cosine of the angle, minus 53, cosine minus 53, divided into 2K ohms gives us 3.32 K ohms of impedance. Okay, so this is the total impedance for that circuit. Okay, so the circuit would be 2K minus 2.65 K ohms would be the rectangular coordinate values. Now we have another circuit here. Again, another simple RC circuit, one resistor, one capacitor, 10K ohm resistor, 50 nanofarad capacitor. We're given a frequency this time of 500 hertz. We're given a source applied voltage of 10 volts. They want us to solve for the capacitive reactance, the total impedance, the angle theta, the voltage drop across the resistor, the voltage drop across the capacitor, and the total current in the circuit. So you can see we're building on the kinds of things that we can calculate just given three knowns here: resistor, capacitor, frequency, actually four, and the source. So again, we start with our x sub c relationship, plug in our values, we end up with 6.37 k ohms of capacitive reactance. We've picked the tangent theta relationship again so that we can plug these values in. Again, you see we forced the negative here, negative 6.37, because we know it's going to be on the negative j-axis. Gives us a tangent of theta minus 0.637. Take the inverse tangent of that relationship. Tangent now is minus 32.5 clockwise. Now we switch to the sine function so that we can use x sub c and z relationships to solve for z. So we're going to take this expression, rearrange the terms. Z now is equal to x sub c over sine theta. Plug in our values for x sub c and our angle theta, 32.5. We get a total impedance for the circuit as 11.9 k ohms. Okay, they want us to solve for the total current I. We know the source, 10 volts. We know Z now, 11.9 k ohms. So the total current is 844 microamps. Solving for the voltage drops across the capacitor and the resistor, we can do it one of two ways. We can use Ohm's law, or we can use the trigonometric functions. Either of them are going to give us the same answers here. Okay, so when you plug in the values, the voltage drop across the capacitor, 5.37, the voltage drop across the resistor, 8.44. You'll notice here again we had the negative value for the angle, since we're in the clockwise fourth quadrant, gives us a negative going 5.37 and 8.44. Again, you have to know and recognize that since we're dealing with an RC circuit, we are always negative 90 degrees. Another one, resistor 5 k ohms, the capacitor 10 nanofarads. This time we have the total impedance for the circuit. Z is equal to 8.3 k ohms and a total source voltage of 10 volts. Again, we've got an array here to solve for: current, theta, frequency, x sub c, v sub c, v sub r. In this case, we're going to start with finding the current because we know both z and the total source, and we get 1.2 milliamps. Okay, back to the trigonometric functions. Cosine theta is equal to r over z. We're given r is 5k, z is 8.3 k ohms. We end up with a 0.602 as our cosine of theta. Take the inverse cosine, we get an angle of minus 53 degrees. So you see we're getting all of these negative values for that theta because that's what a capacitor does. It forces us into that fourth quadrant. Sine theta is equal to x sub c over z. Rearrange the terms so we can solve for x sub c. Z times sine theta is equal to 8.3 k ohms times the sine of minus 53 degrees, or a negative 6.62 k ohms. Okay, so that would be our vector on the minus j axis. We can then take the expression that we've been using for capacitive reactance, 1 over 2 pi fc, rearrange the terms so that we can solve for f. So we just swap in places there. Plug in our values, 2 pi, 10 nanofarads, 6.62 k ohms of resistance. We get 2.4 k hertz of frequency for this circuit. Again, using Ohm's law, we can solve for the voltage drop across the resistor, the voltage drop across the capacitor. Plug in the values. We know the current, we know the resistance, we know the capacitive reactance. 6.02 volts, 7.98 volts. Okay, so Ceres Rc Circuits, where we're able to solve for resistance and reactance. In the next video, we'll cover the inductive series circuits.